Hi,
Okay.
so Chulalongkorn. I'm the flight dynamic team for the CURSR-I project. So this is CURSR-I, our rocket for the Spaceport America Cup 2022. So this thing compete in 10K category, commercial off-the-shelf models. So as a Thai team, we cannot import it or buy our model at Thailand, so we cannot test our rocket here. So a lot of important work goes into flight dynamics, into calculation and simulation to make sure that our design is safe and functional. So the things that make our rocket somewhat unique and gain a recognition being the runner-up for the Dr. Gilmore Award of Innovation is our novel ejection system. So our ejection system would utilize a piston instead of pressurizing the whole airframe. So instead of having like 10 or 20 or 30 grams of explosive, pressurize the whole airframe to separate the components from each other. We use about 0.5 gram of black powder inside this piston. So since the volume that it needs to pressurize is significantly smaller, we can use just 0.5 gram of black powder to push out this piston. And when this piston is pushed out, it's gonna push the whole nose cone assembly out of the rocket. And this way it's open for the drone to deploy. And with the flight computer, we control the tender descender to separate each other, to separate the rope and deploy the main that way. So this is what make the CURSR-I project a little bit uniquer than other conventional design.
Furthermore, the expansion of the nose cone will create a low pressure inside. So we have a vent hole on the side of the chamber. So during the expansion of the nose cone, it will create a suction that pulls the air in, which will push the drogue out. That helps with it. Yeah, simultaneously. That helps with the drogue deployment in high altitude. I'm Patrick. I'm structural engineering lead. And the main difficulties that not the difficulties, but the problem that we face on our rocket development is we have a lot of project and development on different components going on, but the things that stop us from making it is we can't make it possible. In this case, I mean the manufacturing process, the tools, the CNCs. Some of the main things we have to improvise the tools by ourselves in order to create the components that's critical, such as the nose cone. This nose cone was made without the lathe. This nose cone was made without the lathe, and we can even think that if we have the tools that allow us to make such a complicated structure, there will be like many improvement and optimization could be going on this rocket. Like example for this one, we are lucky that we found someone that could help us with machining and CNCs. So this plate was made at the last minute before the flight. We don't even have time to test it, but we know that it will work because from our simulation it will work.
So basically, the problem that we face is that CURSR-I is the first project ever for our club, and our club is just basically established for CURSR-I project itself. So a lot of tools are not ready, as well as a lot of materials are not available in Thailand in the first place. A lot of aerospace grade material we cannot find or procure legally in timely manners, so we have to import it from the United States, making the cost a little bit higher than we would like to. So with this compound with the limited resources available, we utilize extensively 3D printing and additive manufacturing. For example, our nose cone, we entirely laid the composite ourselves, utilizing 3D printing as a mold instead of using autoclave or much more complex or expensive method.
But by developing the 3D printing technology, nowadays 3D printing is everywhere in like middle school, high school, college, or even at our university. By fabricating the composite parts utilizing the 3D printing will allow us to like explore more options to create composite parts without using fiberglass molds or heavy aluminum molds. So, for example, like this nose cone, basically every college, every high school can make such a composite part like this. Like if they create a printing part like that, they don't have to invest on the expensive equipment like Oak just said, which are like autoclave or ENC aluminum things. Yeah. And okay, and another thing that really special about our rockets is we use pretty cheap components. Our processor is only ESP32, which is like $10. We have 2 of them, so it's redundant each other. And the reason why we try to go for the cheapest option is like we try to make the rocket be manufactured in like the cheapest way possible in order to encourage the universities or high school to be follow this way of the guidelines to make the development of the rocket in Thailand be more forward.
So that's the small overview of CURSR-I rocket. So a little bit of a start to end the videos. CURSR-I rocket fly. The max apogee is 11,237 feet, and its top speed is about 0.8 Mach.
Okay, thank you guys.
Thanks.